Cool. Well, I guess we'll just get started. Thanks for coming out. This is the inaugural Project Hub meeting, I guess, which is a new initiative between UBC Launch Pad and the UBC CSSS. Yeah, so we had slides in the initial link. You can follow along if you go to the link with the slides. Again, I'm Kevin. This is Sherry. A bit about me, I'm fifth year honors computer science. I did some machine learning at Axiom Zen, one of my internships. I also implemented ML models for my NW Hacks project. Last year, took 340, highly recommended course at UBC in terms of learning machine learning. And I was formerly an ML tech lead at Launchpad, and I'm writing my thesis on ML, so that's kind of the background for me.
Yeah, and my bio is much shorter, but I'm also a fifth year computer science student. I took Comp Sci 340 1 year ago. I also think it's a highly recommended course, and I'm currently the Launchpad co-president this year.
Right, so the main goals for this talk when I was designing it, I want to discuss the motivations for machine learning, why it's useful, why it's like such a big buzzword currently in the industry, give a short overview of the history of the field just so we have some background knowledge for the field. Briefly touch on various like ML techniques. Obviously, this is a short workshop. I can't go into the entire field, but I'll touch on specifically the techniques that we'll be exploring in the workshop that Sherry's created. Introduce jargon and other terminology, and show that machine learning is actually very approachable. I think there's a big stigma where machine learning is this kind of big foggy concept where everyone's like in awe of machine learning and thinking only like the tech giants can do it. My goal with this talk is to show that you can definitely implement machine learning into your own projects as long as you have good data and it's not actually like a super obscure thing. Really a lot of the gatekeeping comes from, I guess, the terminology and the math behind it, but I'm hoping by introducing this in an like approachable way, it'll be less intimidating and you'll be able to like find resources on your own afterwards. So let's just briefly talk about what is machine learning. This is slightly changed from the Wikipedia description. ML is the study of using algorithms and statistical models to allow computer systems to perform a specific task without explicit instructions, relying on models and inference instead. So what does that mean? Basically, in the past, traditional AI systems were based on hard-coded rules, right? You can think of the early chess AIs. We, as humans, have intuition about how to play chess, right? We want to use pawns and advance them. We want to defend the king, obviously. And so early AI systems that didn't rely on machine learning relied on these hard-coded rules in order to teach computers how to play games or how to do certain things. The whole field of machine learning is about, instead of us telling the machines what to do, to just throw a bunch of data at a machine and have it learn what to do instead. So ML is a subfield of artificial intelligence. I would have loved to give like a huge overview of AI, but this is a machine learning workshop, so I'll be talking about ML specifically. Some applications of machine learning, AI of course. So for example, video game agents, any agents that play StarCraft 2, you might have seen in the news recently like AlphaGo and AlphaZero who plays chess. That's sort of machine learning powered artificial intelligence. Computer vision is a very large field now, especially with the advent of self-driving cars slowly coming to fruition, right? We know Tesla is working on it, Google has their Waymo initiative. All of this is machine learning based, right? They get a huge corpus of video and radar data from the road, and you want the car to know what to do, how to steer, how to not hit people, etc. Natural language processing, so natural languages being like human languages, English, Spanish. It turns out machine translation is something that can be done with machine learning, and in fact, Google Translate now relies extremely heavily on ML and not like human-like translations. It uses, obviously Google has crawled a large portion of the web, and how Google does translations is it looks for websites that have, for example, an English version and a version translated into another language, and just like scoops up all of that data, and that's how they figure out what phrases should be translated as what. And recommendation systems, Netflix and Amazon, two huge tech giants, they obviously have a lot of data, and what they want you to do is they want to recommend you things to buy or new things to watch so that you keep using their services, right? they have a lot of data and they want to do predictions on them to figure out what will keep people on their sites. So let's first jump into computer vision really quickly. Hopefully the sound works for this.
Okay, that's a cat sitting in a bed. The boy's petting the elephant. Those are people that are going on an airplane. That's a big airplane.
Right, so this is a very short clip of a TED Talk performed by Fei Li. She is head of the computer vision lab at Stanford. She also works on Google Brain. And essentially what I wanted to showcase with this example is this was like a 3-year-old child who was given these pictures and the child kind of explained what was in the pictures, right? And so kind of something to think about there is that a young child hasn't really experienced much of the world, right? But they were still able to identify stuff going on here. They probably haven't seen like these specific airplanes before. They're only 3, right? But they were still able to infer that, oh, these were airplanes and these are people who were like approaching the airplane and such. So I guess one of the things to think about there is like, why has it taken so long for machines to get to the point where they can start identifying objects when people can do that already from such a young age with such few training examples? One of them, like a few of these reasons are people experience like the world in 3D, right? We're allowed to move around, we can make inferences about things that way. In addition, we have context about the world, right? We learn that, oh, these are people, right? We don't just interpret things as a set of pixels like a computer does. Our visual cortexes abstract this information away, so we think about things as greater parts of the whole. This is like a clip of what Google's Waymo initiative, a self-driving car, sees. So it takes a bunch of pixel data from video cameras and radar, and this is kind of a visualization of what it sees on the road, and this is like its attempted trajectory. So really, this doesn't seem super impressive to us as humans, but it's a very complicated process being able to identify, oh, these yellow things are pedestrians, these purple things are vehicles, and trying to figure out what's going on, all just from pixel information, basically. So machine learning is kind of difficult. Here's a nice slide, chihuahua or muffin, right? Here's some chihuahuas, here are some muffins, and as people, you could probably get most of them right? Except some of them are a little ambiguous, like if you were trying to explain to a computer precisely what makes one of these things a chihuahua and what makes it a muffin, we run into some interesting edge cases, right? If you were to hard code this kind of logic here, what would you even tell a computer, right? Well, so the chihuahuas are brown and they have 2 eyes and a snout, and the snout and the eyes are darker than the whole chihuahua, except that fits almost all of these examples of muffins as well. So this is why machine learning is kind of difficult, and we want to throw data at the computer instead of us explicitly coding in rules about whether something is a chihuahua or a muffin. So here's a nice XKCD comic where they're talking about this is an easy task, right? Identifying whether a person's in a national park or not, except in the next part of the slide, if you want to identify if something's actually a bird, the other person says, I'll need a research team in 5 years. Basically, this aspect of machine learning is kind of difficult, right? Computer vision, it's still a very pressing topic in machine learning. It's very ambitious. Just for some more history on the field, back in 1997, IBM created a chess AI, Deep Blue, which beat Garry Kasparov in chess, right? This was built on traditional AI. This was not machine learning. This was just a bunch of hard-coded rules for how to play chess, like I was talking about. 19 years later, Google DeepMind created an AI to beat Lisa Dole, or second best person at Go. And a question you might have is like, why the 19-year gap between these two games, right? It seems like they're both board games with perfect information. Why did it take so long from jumping from chess to this other game? Well, we can think about solving the games of chess versus Go by thinking very simply about tic-tac-toe, right? This is an extremely simple game, and the way you would code up an AI to play this game is just enumerate all the positions and solve the search tree to figure out what the optimal move is, right? This is a pretty simple example. The thing about that is, as we go to more complicated games, the space of possibilities expands exponentially. And if we compare the search space for chess to Go, we see we jump from 10 to the 120 to 10 to the 360. And so the reason that we weren't able back in the 90s to create an AI that was possible to play Go is simply because it was too complicated of a game to process just with our naive, like, rule-based AI systems. And in fact, AlphaGo leveraged neural networks in order to, as part of its architecture. And I'll go into this in further detail afterwards. So why is machine learning like at the forefront now? Neural networks and that stuff was hypothesized by computer scientists way back in like the 60s and 70s, but it kind of got shelved, and in the 70s and 80s there's what was known as an AI winter, where people stopped pursuing AI as much and instead focused on other fields of comp sci. So, like, why is ML so big now? Well, I'm going to say that it's two reasons. One, due to Moore's law, we have a huge exponential boost in computing power, right? We finally, at this point, have enough computing power that gives us the ability to crunch through all of this data and have even the possibility of doing real machine learning. The other thing is nice cloud services like AWS, right? Suppose you have just a small laptop at home, but you still want to do ML. We can just nowadays pay money to Amazon, right? And like rent out GPUs and stuff to do this training on. And because of these two things, it's actually feasible for regular people like us to do machine learning on our own, like little side projects and stuff. So now that we've discussed the motivations and challenges of the ambitious parts of ML, we will jump into the basics, kind of the stuff we'll be talking about in Sherry's workshop. So in practice, we usually do ML in Python, and Python will be the language in the notebooks that Sherry's created that we'll be going through. That's mostly because Python's a very convenient language to do data science in, and a lot of machine learning is just taking data, turning it into a matrix, and giving a matrix to some sort of model to train. You might think, well, Python's really slow, right? Like, why do we use Python if we have to do all this math? Well, under the hood, these libraries call out to C. So you write your like high-level code in Python, but it's really running C under the hood to do all the math. And so we still get the nice efficiency of doing things quickly, but we write high-level Python code. So some keywords to maybe take away about machine learning finally are like hyperparameters and parameters. So hyperparameters are things that we as the person writing the model get to choose about the model itself. And the machine learning part of it is learning the models, or learning the parameters. So the goal is that we give a bunch of data to a model, it learns some parameters that help fit the data. We'll understand that a bit more closely in the future, but essentially, this is what machine learning looks like. This is all it is. You have some input data X, usually in the form of a matrix like this, and you want your model to spit out some output Y, right? So this is an example taken from Computer Science 340 slides. So we have an email, right? And we have a bunch of words in the email, and we want to detect whether that email is spam or not. So this is what's known as supervised learning. We have a bunch of data, and we've labeled it whether it's spam or not, right? And the task is that we want to give the model new data, like a new email, and ask it to predict whether it thinks it should be spam or not. That's actually all machine learning is. And so the reason we need a lot of data is so that the model becomes very robust and can generalize over lots of things. For example, if we wanted to train a model to classify different images, right? It wouldn't help if it has only seen one version of an image. We want it to see many different versions of the class so it can make different inferences about properties of those images. For example, different species of dogs, maybe dogs in different angles, so that it gives the model a better chance of understanding what, if you give it a new novel example that it hasn't seen before, you want to improve the possibility that it can detect it. So Another keyword about machine learning is called regression. And what regression means is that we have our input data X, and we want to predict a continuous output. One example of this might be you want to predict the price of a house given the neighborhood that the house is in, right? And so here's an example of some training data. We have this is one-dimensional. We have it along the x-axis, and we want the model to predict the y value of it, f of x, right? We can train some different regressions on this that look like this, and these kind of fit the data pretty well. What this regression means is that if you were to give it an x value here, it's going to predict the corresponding y value on the curve, right? So as we increase the degree of the polynomial in this example, we start to fit the data a bit better. But there's a problem here, right? We could get very precise about fitting the data. We could fit the data perfectly, like for example in this orange crazy curve at the bottom. But as we'll find, we don't actually want to do this because this doesn't generalize well over new data, right? We usually think about, we want the simplest possible explanation that fits the data, because in reality, this curve here probably isn't actually what the underlying data represents, right? It's probably something more simple, like a curve like this. Another example of a thing that machine learning can do is classification, right? So say you have two classes of objects, you have red things and blue things, and then you want to split them into two classes. So we could train a simple model that decides, oh, anything on the upper half of this curve here should go into the blue class, and everything on the other side should be red, right? Well, this doesn't fit the data perfectly. We could fit a different type of model, this green crazy model, that will fit the data exactly. But this is, again, getting into the problem of what's called overfitting, which I'll go over in the future. And essentially, the whole point of machine learning is we want to avoid getting into these overfitting situations, right? We want a model that's robust to new data without looking like this. This is an example of the project I was talking about previously at NW Hacks. We essentially built our app wanted to detect what your emotion was given your facial data. So on the iPhone 10 and such, it gives, Apple has an API that lets you read in facial data and gives back 51-dimensional data. Yeah, Apple gives us 51-dimensional data, but this was a hackathon project, right? We have no idea what these numbers actually mean, right? If someone gave you a snapshot of, oh, this is a happy face, and you just throw these numbers at someone, we don't know what looks happy, what looks sad. So what we ended up doing was training a neural network to decide how to classify these objects. So we took a bunch of pictures of ourselves, basically, and said, these are happy examples, these are sad examples, and the neural network does all the work for us, right? It was able to then classify these things, and this is a representation of it in 2 dimensions. The data comes in as 51-dimensional, and we've reduced it down to 2. And it was pretty robust. We were able to showcase at the end people holding their phones to their faces and being able to detect what kind of face they were making, even though we just trained it on these 80 or so points of pictures that we took. So this is one of the benefits of machine learning, I guess. We don't actually have to handcraft these features, right? We didn't think oh, if your cheek is puffed more than 0.05, you must be happy, right? The model is what learns that. We don't actually handcraft these features. Right, so overfitting and underfitting. This is what I was talking about previously. If this is our data, we want our model to be able to robustly identify things. This is obviously not a great model for the data, right? We can see visually here that the data kind of follows this parabola here. So this is what we actually wanted to learn. The danger is that if you don't think about overfitting, you might end up with a model that says, oh, the curve that you're fitting your data to should look like this. But this is called overfitting, and we don't actually want this because this doesn't actually represent the data, right? This is just variance in the data, and the actual underlying behavior of our data looks like this. And so basically, the way we avoid overfitting is through splitting our data into a validation set and a training set. And we'll go over what this means in a bit, and also in the workshop. Essentially, when we train a model, we give it we've labeled the data, right? If you remember from the past, we've labeled some emails as spam or not, and then we get the model to try to predict. We want it to say that, oh, for this email, we called it spam, we want it to predict spam. But what we're actually going to do is do a validation train split, where we only give it some of the data in training, and then we do some testing on it afterwards. And the reason for that is, if we start training more and more deep models, we're able to get zero error in our training set, right? That's the equivalent of the model saying, oh, this is what the data should look like, and fitting some very specific curve. Instead, if we hold some data from it that the model doesn't get to see while it's training, and then only test against that afterwards, then this allows us to prevent the model from overfitting. So again, this is kind of what this represents. We want to avoid the orange sorts of curves, and we want kind of the green or the red that fits the data a bit better. And in practice, this is what it looks like. So we have our entire data that we want to give the model. We're going to split it into training sets and test sets. And the model will get trained on the training sets, but we don't actually train on the test set. Then there's a concept in machine learning called cross-validation, and what that means is we're going to take the training set and we're going to train it on this and then ask it to predict things on different portions of the data set. And this allows us to kind of be, it keeps us honest about the data, right? If a model performs really well on a certain subset of this data, but not very well on the test set here, then it's a bad model, and we want to be able to identify this. Now we'll jump into some of the specific models that we'll be going over in the workshop. So one is like a decision tree, right? This is a pretty simple like human concept to understand, where suppose we're trying to think about whether we should make a reservation for a restaurant or not, right? So this might be a sort of decision tree that a person makes, right? If the wait time for the restaurant is over 30 minutes, yes, we'll make a reservation. If the price is a certain amount, we'll make a reservation. Otherwise, we won't, right? So we just follow the logic down the tree. And if you're training a machine learning model on a decision tree, what that means is we give it the data, and we're asking the model to learn this branching, right? We give it the data, and we want it to make decisions about what these splits should be, right? Maybe the model finds that, oh, it's more accurate to make a reservation if the wait time is over 45 minutes. And so the process of machine learning is constantly giving data to the model, and it picks the parameters, right? In this instance, the splits would be the parameters that the model is learning. So it's going to learn the best way to represent the data that we give it. So that's kind of what a decision tree looks like. Here's another ML technique called k-nearest neighbors. And so the task here is classification, right? We've given it examples that we say are blue and examples that we say are red. And now we want our model to be able to predict, oh, is this a new object here, a blue or a red, right? And what k-nearest neighbors does is it looks for the k, in this case, in the solid line, the three closest examples that it has seen before, right? And then it asks, oh, what is the majority of these things? And it'll just say, it'll just pick whatever the majority is. So if I set k to 3 here, and I give it this example, and I ask it, oh, what do you think? Is it blue or red? It'll predict red, right? Because there's more red things here than blue. But if I set k equal to 5, there's actually, this represents the dotted line over here, and instead it would predict blue because it's seen more blue things near this given point than red things. So going back to what I talked about before about parameters and hyperparameters, our k here is a hyperparameter, right? It's something that we set for the model, and so it's not something that's actually learned. This is a bit of a technical slide. Another technique we'll be going over is stochastic gradient descent. All that really means is if you have a model that's trying to use a function to predict your input data, you can think about like the error in its predictions, right? By summing over all the errors in the data, and you can say that, oh, this function has an error of this. And so what gradient descent is saying is I'm going to keep tweaking my parameters that I'm thinking of until I get to the lowest possible error, right? This is like a topographic map, and the rings represent various parameters such that the overall error is equal. And gradient descent means we're going to just iteratively keep tweaking our parameters such that we get better at each point. Stochastic just means that we introduce some randomness into the process because basically our error functions aren't always this clean, and so it helps to introduce stochasticity into it. Now, everyone's favorite word, neural networks. We will just briefly talk about what neural networks are. Basically, the problem with doing just regular mathy sort of things, like trying to create functions and stuff, is that if we only model our data using linear functions, a combination of linear functions just results in another linear function, and that's not super robust. A lot of things in the real world can't be modeled by a linear function. And so back in like the 60s and 70s, computer scientists had this idea of building neural networks modeled after how our brains work. And I'm not a biologist, but to a rough approximation, how our brains work is like a series of neurons, and if the action potential is high enough, a neuron will trigger, and the neurons are connected to other neurons, right? And basically, if there's enough like activity leading into a neuron, it will decide to fire too, and that's how our brains make decisions. So people thought, well, what if we just kind of simulate this sort of behavior in the computer instead? So whenever you hear about neural networks, this is basically what it is. We have a bunch of input nodes. This might be, if you're trying to predict things on an image, each of the inputs represents like one of the pixels in the image, right? And in the end, we have this connected thing. This simulates like a bunch of neurons connected in the brain, and then we predict an output. For example, if this output is on, we might be predicting this input corresponds to a cat, right? Or if this input is on, we might say, oh, it corresponds to a dog. And what does it actually mean for these nodes to be connected? Well, each part of the neural network kind of looks like this, where all the things connected into it have weights, right? And so our inputs are numbers, we multiply them by weights, and then we sum them up in each of the cells, basically. And if the value here is great enough, if it's hit the action potential, then we will say it should fire into like the next input. And so when you're training a neural network, what you're doing is you start with a random assignment of these weights, right? And it will spit out some outputs here that probably don't match the data very well at all. And so the training process for a neural network is then the computer's sad because it has a very high error and it doesn't want to have a high error. You want it to have a low error. So then it goes back and tries to tweak these weights a bit more, such that our output more closely matches what we've labeled the data as, right? And so essentially, this process gets repeated over and over until these weights mathematically come out such that our input data matches, labels the output data as expected. That's kind of what neural networks do at a very high level. If you're like super interested in depth, like I'm gonna post some resources afterwards that can go over this way better than I can in this like brief talk. Another thing I thought that would be good to introduce is like convolutional neural networks. This big word, convolutional, all that means is that instead of learning simple weights that we multiply the inputs by, we're learning convolutions. And a convolution is basically a window into the image, right? It just sees a little portion of the image. And so what a CNN is doing is exactly the same thing as these simpler neural networks, except instead of learning like weights, it's learning different ways to manipulate parts of the image. And the whole goal with a CNN is that at each layer, we kind of understand the image at a higher level. So for example, at this layer in the, of the neural network, we might be able to identify lines or like corners, right? And as you go deeper into the network, we might be able to identify faces or like things that look like arms and such. And so the whole goal behind creating systems like this is to simulate kind of how the brain works. If you do any sort of like neuroscience courses, we find that our visual cortexes also follow a similar pattern of understanding images. We start out earlier in the brain as seeing lines and like patterns of crosses and stuff, and this slowly gets bigger and bigger until we can understand like, oh, this abstract shape is a person. Yeah, so if you go to the slides, here's a few things that I think are excellent introductions to machine learning. A couple of YouTube playlists that are really good at introducing neural networks and computer vision. Google has a course on machine learning too, and of course, if you're a UBC student, you should definitely try to get into ComSci 340. It's a great overview of ML too. That's the end of my talk, so hopefully it was sort of interesting, and I'm happy to take questions. Oh, okay. Okay, thanks.
Yeah, you said you were writing a thesis about ML and StarCraft.
Yeah.
So
Yes.
what are like some applications that you can use for machine learning in that game?
So specifically, what I'm working on for my thesis is when we look at replays of StarCraft, it looks like low-level like clicking data of like moving individual units, right?
Yeah.
And so the advisor that I'm working with, his specialty is in algorithmic game theory and that sort of stuff.
Yeah.
So the problem I'm looking into is, can we abstract away from this like unit movie space and move into a different latent space of like actions or like decisions that a person would make. When a person's playing a video game like StarCraft, they think,
Yeah.
oh, I want to attack at this point in time, or I want to defend in this point in time, or I want to expand, right?
Mm-hmm.
And so Blizzard has conveniently released a lot of replays, like 80,000 or something. And so using ML, I'm hoping to be able to train models to identify various strategic scenarios, right?
Mm-hmm.
So I have a bunch of games that have been played, and you just feed that into a model and hope that it can identify different of these like strategic scenarios. We can talk a bit more offline about that, but yeah. Are there any other questions? Yeah.
So can CNNs only be used in relation to images, or?
Definitely the most useful application of CNNs are with images, but I suppose it would work with anything where like convolutions are useful. I think if there's like any engineers here, convolutions are introduced in terms of like signal processing and stuff, right? So probably CNNs would work with sort of audio data as well, but yeah. Cool. Other questions? All right.